Okay, we're going to look into parametric functions. So I'm not going to read to you. You can pause the video and read this first two boxes here to yourself. Okay? So just thinking about the home run, you got your batter here, hits the ball. Here is the fence, right? Here's the path of the ball. Okay, so what happens is, given time, we can know where the x, like the x coordinate of the ball, like how far, let's say after 1 second, when t equals 1, this is how far the ball has traveled horizontally. And then I should write this as, I don't know what the equation is, so I'll write it as some function of t. It'll have t's in it. It could be like t squared or t plus 7, right? And then we'll define the y coordinate separately as another function of t. I'll just call it like g of t or whatever. We could know at that moment when t equals 1 how high. So this would be our x, and the iPad's going to start doing this, right away. This will be our x, and this will be our y. Okay? So after 1 second, you can break down the position of the ball. The ball is actually right here, but you can break down its position into how far horizontally it's traveled and how far vertically it's traveled. I mean, the most common use of this is vectors. If you're in physics and you've done some vector stuff already, that's basically what this is. There's one way to think about it. Another way we've been secretly doing, which is polar and polar coordinates. It's a different parameter. Instead of time, we're using an angle as our parameter, but that is also parametric. So we'll see that come up. All right, so let's just do some examples. I think this statement might be a little confusing. We'll come back and look at it again after we do some examples, or we'll talk about it in class. All right, so graph the following for the given domain. So here's a parametric equation, right? It's defined in terms of the parameter time. So time is starting at 0 and ending at 3. So we're going to try to graph the movement of this object over time. So this just describes its horizontal movement. How far right or left does it move? Like its position after so many seconds, right or left. This equation gives its position vertically, okay? So let's plug in 0 for time and plot the first point. Give me 1 second, sorry. Okay, so when I plug in time here, I start with 0, and I get -1 for x. Just plugging in 0 here. Oops, that's not what I want to do. Okay, here we go. So I'm plugging in 0 here and here for time. So I get -1 and -2. So that's going to be the point that we would graph on the plane, -1, -2. And for now, I'm going to even write that that's at t equals 1 here. All right? So that's our first point. That's where this object starts. So this is called the plane curve that I'm graphing here because it's on the Cartesian coordinate plane, or some people call it the xy plane. All right, so then when time equals 1, I plug that in. Again, I plug in 1 for time here and here, and I get my x and y. So I'm going to get 0 and -1, and I'm going to graph that point right here. And that's going to be when time equals 2. When time equals, I did these, I'm sorry, these are wrong. You're probably yelling at me. That's time 0, that's time 1. So time 0 is where the object started. All right, when time equals 2, I'm going to get 1 and 2. So that's at time equals 2. And then when time equals 3, I'm going to get 2 and 7. Oh, right up there at the top. And that's at time equals 3. And that's the end of the movement of this object. So not only do we know the path of the object when you do parametrics, we actually know at what time is it going to be in what position. All right, we also have to give an orientation, it's called, for the parametric plane curve. So you put some arrows showing the movement of the object. Now, I'm assuming that in between these time values, it's kind of moving smoothly and continuously because these are continuous functions. So I can estimate what's happening by drawing the curve in between the points, and then I know which direction it's going because as time increases, it's moving in that direction of the arrows. That's called the orientation of your plane curve or your parametric curve. So here are your steps to graphing parametric curves. And again, there's the orientation. I am not going to read to you. All right, so now if we come back to this definition, you can see now that we're defining curves in terms of a parameter, and we're defining the horizontal and the vertical in terms of a parameter. The parameter is most often time. We use t. It's so much often time that we use t in the equations all the time, even when it's not time. Just your general parametric equations have t in them, as you can see here and here. And when we graph them out and find the horizontal and vertical component, and we find the location of the object at each time value, we're graphing the plane curve. That should help with that definition a little bit. We are going to do this in class. We're going to learn to use our calculators, so bring them if you have them. Okay, graph the plane curve on here. So this is kind of more of the same, another practice. So let's go through this. If I plug in time equals -2, here, whoops. Right here and here, I'm plugging in a -2. I'm getting 5 and -6. So that's at time equals -2. So how can you have negative time? Well, who knows? Maybe you have a DeLorean. Or maybe time equals 0 means 1955. And time equals -1 means 1954. I don't know. But that's at time equals -2. I'm not going to keep writing time equals whatever next to each point, okay? We're going to just start to know it. So I plug in -1. You can pause this and do this if you want. I'm going to fill them out. All right, so let's graph those points. 2, -3. Right there. Whoops. 1, 0 is right there. 2, 3 is right there. 5, 6 is there. And then it's over because we're at the end of our from -2 to 2. All right, so there's our curve. And now that's our plane curve. Now we want to put the orientation. It started down there at the bottom, and it went that way. All right, now how do we find the rectangular equation of the parametric curve? Now, something to note here, I want to come back to this. Do we say it here? Oh, no, it's later on. Okay. So we're going to do something called eliminate the parameter. So can we come up with the rectangular equation for this curve? To me, it looks like a sideways parabola maybe, but not really a parabola, but we'll see what we can come up with. We're not going to do it for this particular one. But is there, like the curve we're looking at here, is there a rectangular equation that we could find? Rectangular equation means the ones you're kind of used to, y as a function of x. All right, so the way you do that is you first eliminate the parameter. So I'm going to take typically the x and solve for t. So I'm going to add 1 to both sides here and get t equals x plus 1. Then you could substitute that in for your y equation. Instead of t now, I have t is equal to x plus 1. Oops, -2. So then that would be, I guess I'll leave it like this. I'm not going to multiply it out. This would be our rectangular equation. All right, and I know the vertex is at what? -1, -2. There are going to be some questions we'll ask you about this after you eliminate the parameter and come up with your rectangular equation. What's the domain of this function, right? So we know the domain of a quadratic is -infinity to infinity. But I want to take a second and look at this. This would be the domain because it's only the x values. So since there is no restrictions on t t could go from negative infinity to positive infinity. So the domain of our rectangular equation is actually the range of our x here, right? If I can plug in any t value from negative infinity to infinity, what would the output be? What would the range value? That would be all the possible x values. Well, it would be any value because t minus 1 is, its range is negative infinity to infinity. So it's just like a line. All right, so that's one way you can analyze the domain. You can look at the rectangular equation and analyze the domain. It's a quadratic whose domain is negative infinity to infinity. Or you could analyze just the x, the function of x in terms of t, and find the range of that x. It's kind of weird. Okay, now range, we could do the same thing. So to find range is the y values, right? So I can look at these y values and find what's the range here. So again, the t can be anything. There's no restriction. But when you square any value for t and then subtract 2, that range is going to go from negative 2 to infinity, right? So the y values can be as low as negative 2, right? The smallest this will ever be is if I plug in a 0 for time and then minus 2. So the range of this is going to be negative 2 to infinity, and it can be negative 2. Okay, we would know that from analyzing the rectangular equation because I know this is the vertex, and I know this parabola opens up. From Algebra 2 stuff. All right, so I know that the range is negative 2 to infinity. I'm giving you two ways to analyze this stuff. Max, min, well, this is a parabola again, and it has a minimum at the vertex because it opens up. So we have a min at negative 1, negative 2, and there is no max. So I could say I should say the min is at negative 1 and the minimum value is negative 2. And there's no max. Okay, so remember, this is where the min occurs. This is what the min actually is, the minimum value. All right, so the function increases on what domain? From negative 1 to infinity. Hello, hi, how are you? So as I graph this thing, it's looking something like this, right? So I know it's increasing when I go this way in my domain. So all numbers larger than negative 1. It decreases, sorry, wait, this is not decreasing ever. Sorry, it's increasing, yeah, sorry, it's decreasing. It is decreasing. On the left side here, it's going down. So it's decreasing from, those guys tripped me up, negative infinity to negative 1. All right, the function's decreasing as we approach that negative 1 breakpoint. All right, eliminate the parameter, then sketch the curve. So here's one where we can try on our own, but I'll go through it with you. There's no mention of the domain for t values, but I do know that since we're square rooting t, there's an implied domain that t here has to be bigger than or equal to 0. All right, so the domain, oh, they left me a spot here, is since t has to be bigger than or equal to 0, that means what would the range or the output be as I plug in t values? Well, it's never going to go lower than 0, and it's going to be larger, so x will be larger than or equal to 0. Or if you like interval notation, 0 to infinity. All right, there's an implied domain here because of the square root function. And the weird thing, again, I keep saying is when I see the parametrized curve, the domain of the rectangular equation is really the range on just the x. It's the output or the range on the x function of t. All right, so let's eliminate the parameters. So we're going to say x equals square root of t, so I'm going to solve for t. And then I'm going to substitute into the y. So t was equal to x squared. So y is equal to 2x squared minus 1. But we know that the domain has to be bigger than or equal to 0. So you have to watch out when you are asked to graph these. So finding the rectangular equation sometimes makes it easier to graph the parametric instead of having to do the table. The problem is when you excuse me, when you come up with the planar equation, if you don't consider the domain, you might get it wrong, right? I might just, if I didn't consider the domain, I go 2x squared minus 1. Okay, so I go down 1, and then 2x squared is a parabola that's a little bit thinner. So if I go over 1, I go up 1, 2, 3, I think, yeah, it's going to be like right there. Because if I plug in 1, I get, no, it should just be 1, I think. Yeah. When I plug in 1 for x, I'm getting 1. So it should be right there. Then when I plug in 2, I'm getting 7. And it's only going to be this side. And the orientation would be like this. Okay? But if I didn't consider the domain, I would also graph this side of the thing because that's what this parabola looks like. So the rectangular equation, you can't just go ahead and graph it. You have to consider the domain. It only graphs that side, and there's my orientation. And they're just asking where's the vertex? 0, -1. All right, so take a second and read this. You can pause the video. Okay, welcome back. The thing that I would want to know is the graph of the rectangular equation generally will contain more points than the original parameterized curve. All right, so we saw that here. This parametric curve only graphs the positive side when x is larger than or equal to 0. But this rectangular considers both sides. That would be a parabola, you know, looking like this. All right? Let's look at one of these. So find this. This will kind of give us another trick or whatever that they're talking about to using this. So we don't have to use the table. We can use the parametric to get our rectangular, and then we can graph. So this is converting from parametric to rectangular. So now we're getting into parametrics where we're using cosine and sine, and t is an angle now. Even though we say it's time, now with t is bend time, and we're using t still, we're thinking of it now as an angle because we're in cosine and sine here. And it still can be time, but we want to think of it in terms of, because cosine and sine works nicely for us without a calculator in terms of like pi and pi over 2. So you'll see what I mean in a second. One thing that's going to be huge for this converting when we have sine and cosine in our parametrics, right? If our parametrics are defined in terms of sine and cosine, to convert, we're going to use this Pythagorean identity quite often. All right, so what you want to do is you want to generally solve each coordinate, the x and the y, each part of the parametric. You want to solve for the parameter t. So I'm going to take x equals 6 cosine of t. And I'm going to solve it for cosine. Sorry, you don't want to solve it for t. You want to solve it for cosine of t. I don't want to break up the t. So, and then I want to solve the y1 for sine of t. So I divide by 4 on both sides. The reason you want to do that is now we can take advantage of this Pythagorean identity down here. So I need sine squared and cosine squared. I have cosine and sine, so I need to now square each side. Square, 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 and square. So now sine squared is equal to y squared, or y over 4 squared, I'll say, plus cosine squared is equal to x over 6 squared equals 1. So now I can rewrite this as y squared over 16 plus x squared over 36 equals 1. Okay, so that is the rectangular equation for this parametric. Now they want us to graph it, so let's look at the parametric. I know that because we're in cosine and sine, I know that once I get to 6.28 or 2 pi, the graph's just going to retrace itself, right? So this is not the domain of the graph, but I'm just going to go from t equals 0 and end at 2 pi, because I know then it's just going to repeat itself. Because I know the period of these is 2 pi because there's no multiplier here in front, right? That would affect the period. So I'm gonna make my table, because I don't know what this rectangular graph looks like. I don't know if you do, or I should say I do know, and we are going to learn it, but this is kind of a lead into that. Maybe you already know what that graph looks like. I don't know. But we're going to learn that a little later in this unit. So for now, we're going to assume we don't know what that rectangular graph looks like. So we're going to have to do the table method. So we can go t, and then we need our x and we need our y. So we'll go t is 0, t is pi over 2, t is pi, t is 3 pi over 2, and t is 2 pi. So when I plug in 0, again, I'm plugging it in up here for t and getting my x and my y. So when t is 0, I'm getting cosine of 0 is 1, so I'm getting 6. And then when t is 0, the y is going to be sine of 0 is 0, so that's 0. So 6, 0. You start there. Now when I plug in pi over 2 up here, cosine of pi over 2 is 0. 0 times 6 is 0. Sine of pi over 2 is 1. 1 times 4 is 4. When I plug in pi, cosine of pi is negative. 1 times 6 is negative. Oh, I got to graph 0, 4. Sorry, 0, 4. This was at t equals 0. This was at t equals 3.14 divided by 2. So 1.57 seconds-ish. Let's just pretend these are seconds. Okay, really we know it's pi over 2. But I'm just showing you that if you want to think about it in seconds, you can have pi over 2 seconds. It's about 1.5 seconds. Yeah, you could have pi seconds. It's just more than 3 seconds. So when t equals pi, we're at negative 6, 0. At 3 pi over 2, we're going to be at 0, negative 4. I'll stop writing in the t's. And then at 2 pi, we're going to be back to 6, 0. And then it would just keep going around and around. So this is the graph that it makes. It's almost a circle. Kind of looks like a circle. Kind of looks like Stewie, the way I drew it. Mummy. All right, so there it is. I put the orientation on there, and it's just going to keep going around and around and around as t increases. And of course, t could be negative. It would still be going in this direction. It's just we would have backed it up and started at a different spot. It's weird to explain, but it's just going to keep going around and around and around. All right. One other thing is that that's neat to figure out here is that you can make infinitely many parametric equations for the same rectangular equation. You have to be careful, though, again, considering domain. Some things may happen. And so we're going to check that out. So let's get into it. So x equals t. So I'm going to first do this parametric equation where x equals t. Then what would y have to be? Well, if x is t and I want to graph this thing, if I put a t in here, y would have to be t squared minus 5. That would be one parametric that would graph that same thing. What if x is equal to t squared? Now I'm going to do the second situation. What would y be? T squared minus 5. So that would be t to the 4th minus 5. And then x equals t cubed, which would be y equals t cubed squared minus 5, which would be t to the 6th minus 5. So this parametric would make this rectangular equation. This parametric, that's the y, would make this rectangular equation. And this parametric would make that rectangular equation. You do have to be careful for domain. We're going to see that one of these doesn't exactly make the full curve, coming back to the idea that the rectangular equation generally or could contain more points. So you have to be careful about domain stuff. All right? So it says compare your 3 parametrized curves. So let's do this. I'm going to graph them on Desmos. So first, let's graph our rectangular. Y equals x squared minus 5. So there's our rectangular curve. Now to do parametric, you're going to list it as like 2 points, and you're going to use t. Desmos will recognize that. So my x-coordinate will just be t, and then comma. The y-coordinates will be defined as t squared minus 5. So t squared minus 5. All right? So you can see if I turn off the red curve, there it is. But we want, there's no domain restriction on t, so let's make t be negative 1,000. It's really negative infinity to infinity, 1,000. And you can see there is the curve, the parametrized curve, which is the same as the rectangular curve if I turn that off, all right? Let's look at the next one. So I'm going to turn this blue one off. I'll turn the red one off even. So if we graph this next parametrized curve, we got t squared for our x coordinate, comma, then it's going to be t to the fourth minus 5. All right, and then again, we want to go from negative like 1,000 to 1,000. This one is not exactly the same. It's only graphing half of the rectangular equation. So why is that? Because here on our domain, what's the domain of our function here? Even though time can be negative, what happens when you take all your negative time values and square them, it makes them positive. So the domain on this function is going to only graph all the x is bigger than or equal to 0. So this one is not the same. The same thing will not happen down here on this guy. Okay, because when you cube time, you can still get negative values. So this last one will graph the same equation with both sides. All right, so you got to watch out for that. So this one is not the same as the others. All right, so the one where x equals t squared is not equivalent. Oops, I need a v in there. To the rectangular, because only x bigger than 0 is graphed. All right, because we can never get negative x values out of this equation when you square them. All right, so that was the next thing. Let's see what's going on here. Example 8. Find a parametric equation from the given conditions. So they're saying a parabola that has this vertex and opens downward. So let's see, what do we know about our rectangular equation? Y equals opens downward, so I guess it'll have a negative a. And then find a parametric equation. Okay, so I'm just going to use negative 1. It doesn't really tell us what a is. And then x minus 2 squared plus negative 3. So I'll just say minus 3. So there's our rectangular equation, or a rectangular equation. I can't come up with the a because they don't give me another point on the parabola, so I'll just say a is negative 1. It could be negative 5. Add time as a third variable. Okay, so we're going to say x equals time. So there's our parameter. I wouldn't really call it a third variable. I'd call it a parameter. So we can write our parametric equations as x equals t, and then y would be negative 1 t minus 2 squared minus 3. That's kind of the simplest one we can come up with. All right, so now they want us to sketch it. So I know what this graph looks like. It has a vertex at 2, negative 3. So 2, negative 3. I know it opens downward. And I know that it's, let's see, opens downward. I know that it's negative 1. So if I go left 1 and down 1, it'll be there. Right 1 and down 1 will be there. Then I go left 2, down 4, 1, 2, 3, 4. So there, and then there. And then the question here becomes, what's the orientation of this graph? The orientation is going to go this way. Because as t is negative, as t is negative infinity, so you guys are walking into class now as I'm finishing the video, and some people are loud. Ethan? Nothing. And then so when t is negative infinity, we're starting all the way left of this graph. So we're going to be coming up this way, and then the orientation keeps coming down this way. All right, so there's the orientation on the graph. I'm out of time, so we'll do example 9 in class together.